Welcome, welcome to the pre-recording of lecture 32 of Introduction to Supercomputing, scheduled for 8 November 2024. So the plan of this lecture is to explain a simple matrix multiplication executed on Tensor cores. So this lecture is mainly focused on NVIDIA technology, almost actually exclusively on this technology, although there are alternatives available. So let's start with an introduction. So the main application of current high-end graphics cards is on training deep neural networks to and this technology is in some sense also enabling the revolution in artificial intelligence. So training these deep neural networks is computationally very expensive. What this training involves is the evaluation of these neural networks, which involve many matrix multiplications, and that's what the tensor cores do. Also, convolution operations when it comes to doing backward and forward propagations can be reduced to this general matrix multiply. Now, even if we would not be interested in training neural networks, and in some sense in this course in supercomputing we did not touch on this important topic. It is important that the two latest generations of NVIDIA Tensor cores are capable of double precision, and they deliver a very impressive performance. So 19.5 teraflops on Ampere, the computer that we in this course have access to on the Hopper 134 teraflops. So you go from 20 to 134 teraflops in one generation of GPUs. I should also, of course, indicate that 134 teraflops is actually 20 years ago, it would have counted for a real supercomputer. So this is a supercomputer on a chip. In numerical linear algebra, many operations are reduced to matrix multiplication. So that's also the reason why these tensor cores will be a fundamental cornerstone in scientific computing. Okay, so there's one more concept that we need to define. When going through the literature on tensor cores, I noticed the frequent usage of throughput. So tensor cores were introduced on the Volta. Volta is not capable of double floating point precision when it comes to the tensor cores. Now this changed with the Ampere, but if you compare graphics cards with a tensor core, the Volta, to the previous generation, the Pascal, then Volta gives a 12-fold increase in throughput. Now what does that mean? You have a card without a tensor core and then one with a tensor core. Well, throughput measures how much information a system can process in a given amount of time. I'm apologizing here for the obvious spelling mistake in measures, but I think you can kind of get the point. Instead of measuring the peak floating point performance, you actually are measuring the amount of work a chip can do. And in some sense, this is an important notion, and I should have probably introduced this earlier, but supercomputing is often synonymous with high performance computing, where flops is actually a central measure. Although one could argue that in applications you're actually not really that much interested in how fast you can do things, but how much work you can get done in one time period. So this is what they call how high throughput computing. So it is very much related to supercomputing. If you can do things fast, then actually you can do a lot of work. But high throughput performance is also concerned with robustness and reliability. Okay, so this is the introduction. So let's now look into the architecture. So here you see a picture that I've stolen from an NVIDIA white paper on Volta. So what we do have is we have streaming multiprocessors. So the Volta, when we worked with this, we were, in order to keep the GPU fully occupied, we typically needed to schedule multiples of 80 times 64. Now, the Volta was introducing Tensor cores per streaming multiprocessor. So just to recap, to make this lecture mostly self-contained, so a streaming multiprocessor is a little bit analogous to one core on a CPU. So each streaming processor works independently. But the way these GPUs get their massive parallelism is that each streaming processor will schedule arrays of cores organized in bundles of 32 warps. So the massive parallelism is that the regarding now to tensor cores, each streaming multiprocessor has not only cores, general cores, they can also do general work, but you have to keep in mind that they are scheduled in warps, in groups of 32. Tensor cores, there are 8 of them, so we actually do have 640 tensor cores. So tensor cores operate in mixed precision, which I will hope to explain in a minute. Tensor cores are accelerating matrix multiplies and also convolutions, the two main operations in scientific computing, but also, of course, in training neural networks. Okay, we are having access to the Ampere already, and probably I misspoke that the Volta wasn't capable of floating point 64-bit double float precision, because here on the picture it actually says that you have the NVIDIA, but there is an important difference here. So at the left you see how you would do this on a Volta floating point 64-bit floating point processor, and on the Ampere you actually do have the tensor cores. So, and compared, Volta gives a 12 times better throughput compared to Pascal. The 2.5 factor here is when you compare the tensor cores on Ampere versus Volta. Now, if we are going to compare the Hopper versus the Ampere, then we have a 3 times throughput. So the Hopper gets a lot more jobs done compared to Ampere. And you see the schematics, how the matrices, which are these two-dimensional panels, this is a three-dimensional picture, how they go through the cores. And there are more of those tensor cores, so the panels, the fragments, the tiles, they can all get larger. Okay, how does this really work now? So a tensor core computes matrix vector multiplication, and it also accumulates. So you see here this executed, illustrated on a 4x4 matrix. The computations are done in half precision. So typically single float is 32 bits, but this can be executed, this is executed in half precision, so the FP16 on 16-bit numbers, and accumulated again to either 16 4-bit or 32-bit. Okay, so this is a slide that I picked from the Supercomputing Conference 2019. So we have the warp matrix accumulate operations. So they are available on compute capability 7, but you need computability 8 at least. So I have to correct my middle mistake. So I started out by saying that Volta was not capable to double precision for the tensor cores, and indeed Volta has compute capability 7 and 7.5. Our Ampere has compute capability 8.9. So there are some constraints here. So we are not only limited to the multiplication of matrices, but the warp is also very sensitive to regularity. So every threads in the warp, they execute the same code. So there is again this synchronized computation. So in some sense, in the course, I should have said this, we are now going at the end of the fourth part. We still have a little bit more than 2 weeks left in this course. This segment is still on pipelining and synchronized computations. So what is the notion that was introduced with the tensor course? That's the fragment. So I will give an example of a fragment, but here the fragment is essentially a templated type. So we are going to use again C++ to declare a fragment. And fragments are the, if you like, the data types on which these tensor cores operate. So the C++ programming guide will be my first suggested reference. So here you see the execution of one of the sample codes. So it is on the Volta computer. It was in the simple samples. So you can see here the Volta that I have has compute capability 7, and it's going to multiply two matrices. The number of rows and number of columns of all the matrices is the same. So there are multiples of 16. So this is done with a high performance kernel, and you can see that we get double digits teraflop performance in 32-bit float precision. Now, if I'm executing in some sense the same sample, but now it's in samples, and it has been reshuffled to the CUDA features. Ampere has compute capability 8, so it is capable of doing double float computations, but I'm assuming here that this is again done on the same single float, not double float, for a matrix of the same dimensions. And you can see that the teraflop performance is now close to 80. So in just comparing, we're going from 49 to 78. So remember the throughput claim, um, Volta versus Ampere. You have 2.5 factor. So again, scrolling through, did I not so here you see the comparison between the Ampere throughput 2.5 and that's a 2.5 promise, but we get close to that. Okay, so it works. So we do have a tensor core. So let's see what actually really happened. So at the core, we did a warp matrix multiply accumulate. So there is not only the matrix multiplication, but there are these factors alpha and beta. So we can scale the product with a factor alpha and accumulate this with another matrix C. Okay, so we have cooperative thread arrays. So in some sense, when we started doing GPU programming, we have to make sure that our instructions are bundled in groups of 32. But here actually you could see this as a more synchronized computation because the thread arrays, they consist of 8 warps. Now if you do 8 by times 32, then if I'm not mistaken, this could suffice for I'm sorry, so the numbers that are computing 128 by 128, they are divisible by 8 times 32. So also shared memory is involved to store the matrix C. Okay, so the code is, the data layout is such that we are traversing the matrix A row-wise and we are traversing the matrix B column-wise. So we say A is row major, B is column major. And of course, the dimensions need to line up. So the dimensions of the accumulator, the C, is the same as the dimensions of the resulting matrix D. Okay, that's one slide explanation of what just happened, what we executed. Let's now go a little bit more in detail on how it really worked on a simple matrix multiplication. So I'm following the demonstration code that was posted on a technical blog, advertising the CUDA 9. So I should say again, there is the version numbers of CUDA. So CUDA is the Compute Unified Device Architecture, the programming model that is defined by the NVIDIA for the NVIDIA cards. So we have the compute capability, which is hardware oriented, and you could say that the version of CUDA is of course software oriented. Okay, I executed So this is all highly technical and very quickly evolving, but I executed the same code that I downloaded from this GitHub repository. I executed the same code on the Volta and on the Ampere. It's no change at all. And it worked. I will give the output. Now, the first mistake I made was not downloading the makefile. Please also, when you do this at home, download the makefile. And because the makefile contains the instructions to compile. Okay, what is the purpose of this blog and also the purpose of the remainder of this lecture is actually show the use of this application programming interface, the warp matrix multiply accumulate. So it is technical and it will take some time to get used to, but in some sense we are always doing the same operations. So there is of course two um, warnings here. If you really have to multiply many matrices, don't use the code that we are showing here. So I just executed the CUDA Tensor core, what comes from the sample CUDA toolkit. Now, as before, as what we also explained earlier on in the course with the matrix multiplication, you get the best performance with the CUDA BLAS libraries. So use those if you really want to use this in production. So the purpose of this blog and what I'm following also here is to explain how it really works. Okay, so there are 4 steps. We're going to use C++, so we have to make sure that we are using the namespaces correctly, that we include the headers. So there is the stage where we declare and where we initialize. So we're going to organize our threads. Recall the matrix multiplication that was accelerated by NVIDIA CUDA. We were using what became a 4-dimensional organization. We had a 2-dimensional organization for the blocks, and we had within each block we had a 2-dimensional thread organization. So that is also done here, and it's good that we all remember these lectures. So the organization in threads must match the organization of the data. So that is the organization of how the threads are mapped onto the data. Very important second step. Then we're going to do the matrix multiplication in the inner loop. So in some sense, the inner loop, there's only one inner loop, but keep in mind that we're going to launch a 2-dimensional grid of warps, and in some sense, if the if everything works out right, so a matrix multiplication is very compute intensive. It is cubic in the dimension, but there's only one loop. So actually you get the illusion that you can do matrix multiplication in linear time in the dimension. So that's also why perhaps the whole artificial intelligence revolution is so magic. We actually have at the technology level, we have managed to take something that is cubic and make it linear in the data. Very important last step, make sure that you get the data that is in the accumulators, in the fragments that are accumulators, that they get into the global memory of the GPU. So that's the finishing up stage. Of course, we always have the transfers from the host to the device, from the device to the host. Okay, so this is the general outline. So there is a 4-step process here. And let's now go through these 4 steps. Okay, so we have a fragment to declare. So it's a templated type. What will you declare? So a fragment can be the A, the B, or the accumulator, the C. We have the shape, number of rows, number of columns. We have the data type. Will the fragment hold something that is a single float? Will it be a half float? And we also have to specify whether the data is organized in rows or in columns. So the templates allow us to define in the same fashion many different things. So we have different shapes, different matrices, A, B, or accumulators, A, B, or C. We have the different data types and how they are stored. At the end of or following the declaration, we're going to fill the accumulator fragments with zeros. Okay, so here is how it goes. So as you are following through this YouTube video, you could, and probably should have said this, you could have gone through the GitHub page if you have not clicked on it and go through the code as I'm just explaining this on the slides here. You can also, of course, read the blog. So we have these less than, larger than, and here you see the names of the fragments: A fragment, B fragment, accumulator fragment, and then C fragment. So we actually have 2 accumulators here. We have our A and the B. The A and the B are both stored column major. So that will be important later on. This could be very convenient if you, from the host, you transferred the data from, if the data was indeed organized in columns. Now the inner loop. So again, why do we call it an inner loop? We have a cubic computation that is reduced to a linear one. So we run over the rows of A and the columns of B. We load in the data from the global memory onto the fragment. So the global memory is the memory on the card. The column major, row major matters, and I think that this might have been done on purpose here to store both the matrices in column major, even though it would be better to do row major, column major, row for A, column for B. But by doing them both in column major, we must provide a stride to skip the number of rows in case things are column major. The A is column major. I hope we can observe this when we are loading the data in the fragment for A, that we have to provide a stride. The initialization to 0 is very important. So this last bullet point emphasizes this. So why do we do this? Well, it is accumulated in place, which actually means that the data stays in the fragment. It doesn't go back to global memory until we finish up. So the initialization has to be done. That's important. All right, so here is now the actual code. I mentioned the include, so we have the matrix accumulate header file that we include, and we are using the namespace provided by the NVIDIA CUDA. Everything must be a multiple of 16. I haven't actually checked this, but if you're good with arithmetic, then you can verify that 16 by 256 is indeed 16,384. We also have the dimensions that have to be 16 now. So this seems to be currently. Now the current is as of 2017 in CUDA 9. So the current versions are CUDA 12. So it's more than likely that you can do a lot more already with the latest CUDAs. Okay, now comes the kernel. So here you see we have this general matrix multiply. Assume that the matrices are in global memory. You can see that A and B are half precision, 16-bit floats. The C is the 30-bit float. Also the result here. So you can see that the C in this documentation here appears both as the accumulator at the right and appears at the left. So we have the accumulator defined from the fragments, and then we have the accumulator in the argument. So perhaps you may have wondered this, or at least I wondered this. So we have two C's here. We have an accumulator, we have two accumulators. One accumulator that is the result, the C fragment, and then the accumulator fragment. And the accumulator fragment at the right is going to be initialized to 0. Okay, then the leading dimensions, which in some sense are all the same here for this example, but typically they are the number of rows for A, the number of columns for B. The result is also stored row-wise. So here it might not matter because in the example M, N, and K are all the same. Okay, now it gets to the inner loop. You see, we're going to loop over the K. We are computing the rows, the columns, indices, loading in the fragments. So you can see we are loading in from A and loading in from B. And then we do the matrix multiplication. So I was telling that I would point at the stride when we are loading in the matrices. We are loading in the matrices row-wise and starting at the beginning of the matrix A, at the index there, and gradually increasing. So the parameter here that increases is the I. Based on the I, the column and the row index is adjusted. All right, we are doing the matrix accumulate. The sync is in sync with the fourth part of this course, which is called synchronized computations. That is basically it. So that is in some sense we have arrived at the heart of the computation. And I'm realizing now that I haven't sufficiently prepared this to explain this in much greater detail. So I should stare at this a lot longer, but I invite you to do this and I continue to the next part. So we are doing not only a matrix multiplication, but we are scaling the product with alpha, and then we so the alpha thing is happening here, you can see after loading in, and then we're also adding up that with beta. So we're loading in the fragments for the C from the um, accumulator. So you can see here that the C underscore fragment is really the accumulator in the C equation. We are multiplying this with beta. Okay, and we are using it in both ways. So the accumulator is used both at the left and at the right. There is the enrolling, so instead of having this as a loop, the compiler will generate all the instructions one after the other, saving us the arithmetic. Will most likely then also compute automatically the offsets in the data structures. Very important not to forget this, to store the fragments into the C. The C is what is the um, result that will finally end up in the global memory. Okay, I'm close to the end now. So I ran this both on Volta and on Ampere. So this is transportable code in the sense that transportable from one generation of GPU to the next. No changes were necessary. Now there is the warp matrix accumulate that is compared to the CUDA blast. So if you're interested and if you're going to run this in production code, do not use the simple matrix multiply, but use the CUDA blast. And here you see something quite interesting again. So the simple matrix multiplication improves a little bit on Ampere. I mean, you have some improvement, but you here kind of see also the point of the course. If your code is not very efficient, if you have inefficiencies in your code, they're going to be multiplied. They're going to prevent you from having better results when you are using more powerful computers. So in some sense, the misunderstanding with supercomputing is often that you can afford to be a little bit inefficient. The answer is just no. So because you can see that the CUDA blast improves a lot more than our simple matrix multiplication. So the CUDA blast again, optimally or close to optimally, or nobody can do it better than um, this library. Okay, I will end with some suggested reading. So I refer to the C++ programming guide. Also look into the white papers. So everything is focused on NVIDIA. So I took a lot of material that is available there. There is a more extensive paper that appeared in the proceedings of the IPDPS that is going to explain how this matrix multiply works on tensor cores. So this is a more in-depth research paper. There is the third paper that is written by vendor agnostic GPU computing. Um, so this goes to the Julia programming language. So this is also suggested reading. So I am myself not yet confident enough to attempt something similar in Julia, but there is the package GEMM kernels, which is written by the first author. and which is available also on GitHub, and you can install it. Then the last reference is more for people interested in numerical analysis. So you may be a little bit skeptical or suspicious on how this mixed precision really gives you good results. It seems like a trick that hardware people do, but is it really sound? Well, I invite you to read in this last paper that will do an error analysis. Okay, I have only two exercises. I kind of stated that if you can do matrix multiply, you can also do convolution. So think of convolution. So I have two vectors here. Think of them as the coefficient vectors of two polynomials. So we want to multiply polynomials together. Can you rewrite this in matrix product? So this is a paper and pencil or pencil and paper exercise. Verify that indeed you will get tuplets matrices out of that. So there is a paper and pencil exercise. There is an exercise that is more computational. So install this Julia package, GMM kernels, and see, so the package documentation also has tests in there. See if you can do some actual computation with this. Reproducing what is in the paper is too much, but just similar as I in this lecture ran two different types of codes, just also run something and see whether it works. So I hope this is interesting. So me myself, I'm fairly new to this new technology, but I hope that it got something that it explains something worthwhile to you. So this is the beginning a little bit of the end of the course. It's kind of the next to last lecture in this fourth part of the course. In the last part of the course, we go more into applications.